For the agenda?
Yeah.
Yeah, I think, well, given that Maria's about to go halfway around the world, and I can give you the rebounds first.
Sure. I'm just having issues to connect to the Wi-Fi. But I can use another computer. I can
Yeah, you can use this computer to navigate if you want.
Yeah, sure. I mean, I didn't prepare anything in particular for
No,
this
no,
meeting.
it's not.
I
Yeah,
just the book that I have.
that's
So
mostly yeah. Yeah.
yeah, the libans is that there's a stereo command that they just run the bounds, but you can add. I think the issue was that you can add covariates. So I can did like create the bounds manually. So there's a paper that I wanted to send you all, but I haven't yet. That describes the steps behind the command or behind creating bounds, and I should follow that. It's nothing very special about it. But you can go. I don't know if you want to actually like should we share screen or you can all open the code.
Yeah, maybe probably best because it's being recorded. So
Are you all hosts?
I
I
think
think
and the host.
Can I click it? I want you to have a link to this.
It's,
Oh. Okay, yeah, let's go. No. Yeah. Go.
Okay.
So is there a shell for this in the way that?
It's not a shell, but it can be easily adapted, I think. I mean, I created for an employment paper, but it's so if you go to VSY, I can move this, or we can make a copy and make it a shell in a different folder. But now it's in my personal.
So is rebound like similar to indents and Rubens? Or is it trying to do something with null effects?
So it basically makes it's like the more flexible or more like I think it's an approach that makes very not that many assumptions. So you just assume that every non-response is from one group or the other, and then like trim the data from the highest and lowest level, and it creates bounds. So you know that it's gonna be within those bounds.
I see.
But
so it changes the sampling structure based on some non-response patterns to produce lots of data estimates, and then you have now a range of data estimates.
Maybe you should show your employment paper.
yeah, but let me open this paper. Yeah, so this paper basically explains what is behind this procedure and how to do it, and this is what I follow. There's also the official lead paper, but it doesn't. I mean, you can read it, but it doesn't go very detailed. I mean, not like in a practical point of view. But this here you have like the intuition the estimator. I'm not an expert, so maybe it's easier if everyone reads it. So yeah, it's like a range, and you know the treatment effect is going to be within that range.
Based in baseline characteristics.
Sorry?
Based in baseline characteristics of the non-response.
No, based on, I mean, the only two assumptions are random assignment of treatment and monotonic. There's really no assumptions or no nothing special. So it
It's just like
trims,
trimming it right
yeah,
now.
it trims either the treated or the non-treated observations. So that the share of observations is equal in both groups, and you trim from above and below. So you make the assumption that those who didn't respond are all, like, let's say for the employment paper, they were all employed or all unemployed, and then you know that the effect is gonna be in the middle. And now, so this is a silo, my personal folder, syntax for the labor paper. The one with page, we were adding weights, so let's say with H3, and this is sensitivity. I'll make a copy. So basically, maybe I should show you the paper too. But this is the sensitivity code. So it just creates a table that has by weight the main estimate. So the full one with covariates and everything, the one that's presented in the main table, then one without covariates, then adding weights, and then the two bounds. So the main specification, non-response weights, and then Lee bounds. I just follow the steps from this paper that I showed. So you first have to find the selected observations. So it's just the n, the number of responses, the sample size that has a response for the variable. And then you calculate the proportions that you have to train. And this is the way to do that. And then you find which group is the one that you want to train. And usually, as expected, it's usually that the treatment group suffers less from occlusion in the FY. You should always test that, I guess, for each outcome, but it should be similar. And then you get the number of observations that you need to remove. So this is not a shell, but it's kind of a shell because it's always local, so it's easily you can easily adapt this. And then you're gonna train the treatment group because it's the one with less attrition. And you create the variable in which you want to run the regression. So first it's just the same variable, the original one. So this is gonna be the upper and the use upper and L from lower. So we're gonna create the two bounds. First, just defining it similarly to the original one, and then you replace it as null, as a missing value under these conditions. And then the same for the lower bound, just with the other direction. Yes, sorry. I don't know how to use this or not.
It's working in a PC environment. Okay.
Wait. Right. So after you train the treatment group, you just run the regressions for these new variables, the lower and the upper, with the covariates, because with the covariates and effects as we use it.
And you make this independently for each wave. You don't start with them.
So I did this by wave, and then for the combined analysis too.
It's different. There's rules for your paper.
No, I mean they're all move basically, and then there is this significant effect at wave 2 in the intensive margin, and that's still you can still detect it with the bounds. This is just how I was presenting everything that has the effect in percentage points too. And then this is the way I was also trying to mimic the way that the Liban command will present it. It has at the bottom of the table, it shows the number of selected observations. That's basically the number of observations with data, the trimming proportion, and the total observations. That's 1,000. So I added that at the bottom of the table.
And the trimming proportion is up for your discretion, or is also recommended in the paper to have a specific proportion?
So that's calculated here, is this formula. So it's like the number of observations that have value, divide, like for each group, you do the number of observations with values, divide by the total, like 400 or 600, and then like the proportion of in this way.
So intuitively, if the high cash group has a response rate of 90% and the treatment has a response rate of 95, the trimming should be the difference between those and only 5, or the full extent of the largest, which is the control group, for 10%.
I think it's something like that. So the treatment group has a 5 percentage point high response rate. So you trim the treatment group
On that difference.
on that proportion. Yeah.
So that they both become 90% response rate.
And then you remove from the outcome of the treatment group. You sort the data. So if it's a continuous variable, that's more intuitive. If not, in a dummy variable, which has more ones and zeros. But if it's a continuous variable, you remove the highest and the lowest values.
See, so in your case, if the outcome was employment,
Yeah.
the 5% that you're trimming is going to be all
All of the
ones or all zeros
Right.
for the lower and upper bound.
Yeah, exactly.
What does Lee argue in terms of like so it's solving the problem of attrition or differential attrition?
I mean, what it's doing is just giving you a range that you know pretty sure, like with very minimum assumption that your type is gonna be within that range. But it's likely that it's gonna be a wide range if you have more attrition, obviously. So it's not super helpful if you have a lot of attrition, because it's gonna be like the effect is gonna be between here and here. But the good you don't have that.
Yeah, I was just gonna say, I think it helps with giving some magnitude to the uncertainty of the unknown.
Maybe you should show.
Like, how bad could it be, or how good could it be? Given the uncertainty of the unknown.
And coming back to our example of the difference of 5% response rate, the upper bound is excluding the top 5% in the treatment group, and the lower bound is excluding the bottom 5%. And then calculating those differences between treatment and control after trimming those tails. Okay. Very similar to what we were doing with Greg before calculating the implicit bias.
Do you have where? Can you
So,
go to the-
I've got it. Can I share my screen?
Yeah.
Okay.
As a thought exercise, I wonder, is it like just as equivalent to say like add fake observations to increase the number of observation in the control group and give it the 5 highest values or something like that? And then give it the lowest,
Yeah. That is the same.
whatever, 5% of the values. And that way, that's right. You have more power, but it's effectively, I think, trying to do the same thing by balancing off the response rates and manipulating the outcome. But you have more precision. I don't know if it's good precision. But I'm just like, theoretically, you can go in either way. Why go with the subtraction approach when you can go with the addition approach?
I don't know, I guess it's the most conservative one,
I
but
guess-
I don't. But see,
Failing.
I think it's right here.
Okay.
Where's the Dropbox folder?
Yes, theoretically, you are now entering the education realm.
Yeah.
Offering all those assumptions.
Yeah, yeah.
Okay, kind of combine the Nancy balance with the approach that they take here. I mean, because the Nancy balance makes no assumptions, but then they like include like the highest value, so they're able to do that. But yeah, I don't know.
Yeah, I don't know.
Mhm. So this is the table that I was saying, has the main result, like the same from the main table, removing covariate, non-response weight, and then the rebounds. And then the outcomes are on the. So with employment papers, basically all things small except for wave 2, the working full time. And here you can see that the rebounds are between minus 0.6 and 0.9, both significant. And here, like at the bottom, for each outcome, you have the selected observations. So the size of the sample size that has values, and then the trim proportion and the total observations that you should have without attrition.
Then the next page. of the
And then,
table.
so this is by wave, and then the full one.
So there's no selected observations of the portion between numbers.
Right.
Is that because it's pooled?
No, I guess that's a mistake. I should review.
But it's interesting for the pool then, there are like two ways of trimming, right? You can trim within wave and stack. And then you can just trim across the waves and you may end up with slightly different results. Right? You know what I mean?
Yeah. I don't know which one.
I don't know. I would assume trimming within wave is more, I don't know, it seems somehow more logical, but can't. Apparently not, because I can't articulate the logic, but.
If you did it across waves, we kind of have to be done.
Greg and Paul, could you guys just speak up a little bit? You're a little challenging for me to hear. I
Yeah.
apologize.
All right, so the question was, in a pooled analysis, there are two ways of trimming, right? You can trim wave 1, wave 2, wave 3 separately, then stack it, and you will have equal response rates. Or you can trim by having first pulled it, and then trimming the observations at the person by wave level. And we're talking about which is the more valid way, and somehow it feels more valid to trim within wave than stack instead of trim across waves at the person by wave level. But
I think, doesn't it in part hinge on whether you're doing within wave fixed effects as well?
right.
Right, so yeah, if you're not doing, yeah, I'm just
I
putting
think-
that out there.
So I should combine the ones that I created by wave separately. So
But since the covariate list includes wave indicators, as Catherine pointed out, maybe it makes more sense then to do the trimming within wave for that reason too. I didn't provide a reason, but for that reason.
Call you intuition. Good enough for me.
Cool.
Any more thoughts?
Did you get any reactions from like the people who see the results and the lead bounds? And did people respond to the lead bounds in a particular way that gave some insight into what this was doing?
They didn't comment, even the reviewers.
Right.
They did, I think they liked it. I mean, if we didn't have them, maybe they would have accepted to create them, because at least one of them, like when they describe the result more as like to the editor, like they said like, oh, and they did rebounds and that. So I think this is something that they valued, but they didn't really like pay too much attention.
I didn't pay any attention.
Yeah.
Right? There was no, but they're, they're unusually informative.
Yeah.
But not very informative. When you look at the ranges, that you don't change your impression of any of the basic results.
One immediate question I had when I heard bounds was,
But we also have she's working with such high response rates.
Exactly.
Yeah.
yeah,
So I think it makes much bigger differences, and I don't know whether we'll be in this world or not, when there's a lot more missing, when there's a lot more uncertainty about what
right,
So the balance will be less informative.
right. They're not so sensitive. So like, and I guess it makes sense to focus on just the beta estimates from the bounded estimates and not the standard errors, right? Like, because one might think I'll take the lower confidence interval from the lower bound, and then the upper confidence interval from the upper bound, which exaggerates the range. And maybe there's some interpretability of using those edge bounds, but maybe not.
That's what he does in the paper.
Oh, okay.
Like he goes through the process of like how he can, like how he like generates the standard, or estimates the standard errors, like there's these different components to get them, but then he does that where he like basically provides these estimates of like, yeah, exactly that, with the lower.
So
the
confidence
interval.
he presents the confidence intervals for the lower estimate and the upper trim estimates.
Yeah, so he presents both like the bounded estimates, but then also the confidence interval in the way that you described.
I see. And he interprets it by using the lower confidence interval bound from the lower bound and the upper confidence interval bound from the upper bound to describe the range.
Yes.
That's not a good for this paper.
but that comes with, that makes no sense. Right, like, because all points in that range are not equally probable.
Right.
Yeah, but it's also, I mean.
But also, Nick, when you're talking, could you just lean in and be louder?
Yes, I can.
We can also change the source of the mic to
Yeah.
this computer because it's closer.
Yeah, we can do that.
You can just bring that computer up, right? Because
But I think the mic also is.
do they want to see us all, or do they want to hear?
I enjoy seeing you all. It's lovely.
But you'd rather.
I'll hear, and then can you kill the speaker there? Okay, Catherine, can you it's better now?
Nick, can you talk, Nick?
Yes. Can you hear me?
Say 3 words.
Can you hear me?
Yeah,
Kev?
that's better. Yes, thank you.
Okay. Cool.
Some president 100 years ago, somebody came up to him and said, I bet my friend I could make you say 3 words. And he said, you lose.
Nice. Okay,
Okay.
Moving on.
all right. Trying to figure out what's helpful in terms of weights. Is it the coding implementation that would be most helpful or no?
No, I think we have a very specific question.
Cover that.
which I suspect you'll be able to answer just very clearly. And this is, and Greg, please reiterate if I get the question right, or reword. So, we know in the Twang package that it does a lot of interactions to check and try and achieve balance. Let's just do the balance one. No, let's do the non-response one to get it back to 1000. We had the question / concern about how carefully the algorithms would be able to assess and then replicate the fact that non-response in the control group, the low cash gift group, might be differentially determined, predicted than non-response in the high cash gift group. Like, does it model them separately? Does it model them together and you get a mix of the two?
So the answer is neither, but way to force it to do it is to compute the non-response weights for the treatment group, right? And then to do it again and repeat the process for the control group. And we've done something similar to this, where like when you, Catherine, Molly, and I were first working with the weights, a similar question came up with sites, right?
Yes.
Assignment is within site. And typically when you're using like a traditional propensity score model, you would stratify them by sites. And you can do that by subsampling or by interacting with the site indicators. And what happens in Twang is because it's not using a linear projection, right? It's using what's referred to as like boosted gradient models or generalized boosted models or gradient boosted models. And it uses some function of decision trees where it's like splitting people up into lots of different mini samples of like, are you male, female? Is your income above X or below X? And all of these things in various iterations.
But then once it does a split, it looks within the two groups.
So it uses,
split.
well, so what happens is I don't know the exact model, but the process of identifying the weights includes various interactions. So you could imagine that there's a tree that splits people by are you in treatment and control, or somewhere along the way, are you in treatment or control? And so treatment is likely, there's a high probability that treatment is being interacted with these other things to say, or with site to say that it's sort of being accounted for, but not mechanically so, right? To mechanically account for them, you would just subsample to see differently. And so for the sites, Molly's prediction was that it would not matter whether we stratify them and run Twang 4 different times versus like running it all at once, because her prediction was that it would be interacting site with all of these other covariates in the 10,000 iterations that we're running at some point, the one that is the most optimal. And to arrive at the most optimal one, it's probably going to have to be interacting with site. So that was her prediction. And my prediction was, it's hard to know until we get there. And I would like to try it. And so I ran it 4 different times using the age 1 data. And lo and behold, we got the same results, or like not identically the same, but the results were not sensitive. But I guess the open question is, we did that with age 1, which had a very high response rate. And so it may be that whatever we did, the results would not have been sensitive. But with the age 4 child outcomes, it may be, and I'm not sure.
Yeah. So probably the first step is to take, and the maternal survey, again, it's pretty, I mean, there's differential response, but it's still overall, it's 88%. It's going to be different when we get down to the like 72 versus 84% for some of the child assessments. But as a first pass, Nick, it'd be super fun to run the weighting shell for the age 4 maternal survey, just in the way that Paul described, like separately for the treatment and control, and then again, everyone all together, and see how different estimates look based on weighting. And in fact, we haven't run that shell with weights. Yeah, anyway.
So with Twang, can you force a partition right off the bat?
Well, you stratify, you have to stratify the sample. So you say 400, you need to be like, or, 384, you need to be like the 400.
Right.
But looking for these differential predictors within the two groups.
Yeah, it's a within group weighting.
So there isn't a way to have a sample of treatment and control, then run Twain and have the first split always be on treatment. I think I don't think it's possible with R's version. R has more ways to customize the setting and the output, but I don't think I've seen one where it allows you to mandate that first splits must be treatment control. And so you would just do that as a user by just parceling out treatment samples and writing it. And I suppose you could do that with other features like treatment and insight or whatever. But one trade-off that often happens, I think, with using like fixed effects type of things in weights is the quality of the weights are not as good when you do it that way with more stratification, because there's less information to be like waiting on. And so there is a trade-off, right?
There's less information if you do what?
If you do the stratified approach. But I think that, so like, let's say like for my virtual charter paper, we had like 500 neighborhoods, and like we take a subsample of neighborhood 1 and try and match between treatment and control or something like that. It might be different for the non-response weights, but like as opposed to putting them all together or running the equivalent, putting them all together and adding neighborhood fixed effects, as opposed to running the weights without these fixed effects. The quality of the weights are often better without these fixed effects because the matching range is greater, because you can now pick from people outside of your fixed effect, and maybe that balances the covariates better. And so from I don't have an extensive understanding of it, but from what I understand, there's always been this trade-off in the weighting world by including fixed effects in your weighting scheme and then not including them. And I suppose my suspicion is we're going to have a similar problem when we separate into the 4 sites. And so there's some trade-offs there that
Yeah, the 4 sites is probably even worse in some sense though, because some of them are so small, right? Like you have like, yeah, I mean, that's like cutting the sample 4 ways rather than, 40, 60.
Yeah. So it's hard for me to know like which one is the more valid one in that case, but there's a trade-off that, yeah. And it was nicer with H1. It was so inconsequential and I ran like 20 different iterations, and
We
Catherine
did a lot. I'm having flashbacks. Yeah, I'll work hard on this.
It was,
Why is site a featured split?
because random assignment was within site, and so one might think of this as 4 different experiments independently run.
Not Greg.
Why one? Not Greg.
But I don't know, it seems like in general, you want flexibility in subgroups where you're likely to find differential predictors within those 2 subgroups, right?
Right.
And I would worry most about treatment and control. I could worry about site, I could worry about well, any number of other characteristics, baseline characteristic, low education, high education, things like that. And I'm just wondering why site gets put in a, would you privilege site as much as treatment control difference?
No, I would not. So like, and I think where we had settled on was we should just put them all, we shouldn't stratify them separately and just use them all together and let the fixed effect indicator kind of resolve this. Is kind of where we landed. And in my virtual charter paper, the weights include these fixed like indicators all together. It's just something that happens in the quality of the weights, in the balance you're able to achieve when you do them. that for some reason you can sometimes lose the balance more if you include them. It's
And I think I'll just throw in, I think there's a world, and I don't think we're exactly in that world, where like if you knew things differed by site, like suppose we thought the hurricanes in New Orleans were really driving different patterns of non-response because people have moved. And maybe it's the most wealthy people that have moved out of, things like you could come up with stories where you would think that, but I don't think we're not in that space with clear ideas about why non-response should differ by site. Whereas we are perhaps in, we have concerns about why non-response would differ by treatment in a high or low cash gift group.
right.
So we should certainly experiment with partitioning the samples that way. Right?
Yeah,
And then
yeah.
doing the analyses separately,
I think so.
even if we end up pooling them and letting Twain essentially find whatever
Right.
differences it would find.
I think so. Yeah.
And then, so you've got these weights separately for the two groups. How do you normalize them to be the same? Is it, you set the average weight proportional to 600 versus 400?
Right. I don't know the answer to that question because like what happens if I think, well, I'm not sure. My guess is the first thing to run after you create the non-response weights is to summarize the weights to see what you're getting.
Right.
And if, let's say in the treatment, I think you should end up with 400. I think it's like, if the full sample is 400, the sum of the weights should arrive at 400. In which case there's no more
Right.
adjustments to do. And the control group, the sum of the weights should become 600. And so you'll have a sum of 1000. And I think that should work. The one thing I had vaguely worried about, but just didn't put a lot of thought into is because the two weights are coming from the separate weighting models, is there a one-to-one equivalence? Which I think is the question you're asking about. Is a weight of 1 in the control group sample weight equal to the weight of 1 in the treatment group sample weight?
But you don't quite want that because you want them 60-40 and not 50-50, right?
Right. No. Like what's when I say 1, like if say like some of the respondents are going to get a weight of 1.2 or 1.3 and they sum to 600. Does the 1 in the 600, is that equivalent to 1, whatever 1, the value of 1 is provided in the treatment group? And you want that to be 1-to-1, not that the groups are 1-to-1, just that the value of 1 in one group is equal to the value of 1 in the other group. And I think it would be, and one sanity check to make sure that that is true is to do a summary of the weights, that one group is giving you 400 and the other one is giving you 600. And if it's not, then I think you have to do some scaling.
Right.
And you can scale it so that you arrive at a sum total of 600, and you can scale the other one so that you arrive at a sum total of 400. And the scaling factor might be a little bit different, but it's easy to compute that scaling factor.
Right. The other calculation is what the range of the weight within the group is, the relative range. Right? Is it 4-to-1? Is it 10-to-1? Is it 100-to-1? You're going to be weighting cases
Right.
differentially, even if they sum to 400 or 600, right?
Right.
And the more variable the weights, the bigger the standard errors.
Right.
So you don't want huge
Right.
weight variation and weight value variation.
Right.
And if you do this with a simpler kind of case of
Yeah.
sampling, differential sampling, right? You'll have samplers often do weight trimming,
Yeah.
right?
Yeah.
To reduce that potential problem. I
Yes.
wouldn't think it's going to be much of a problem here because you're getting these predictions based on
Yeah.
the models, but it's something to check for also.
Right. So this reminds me of like a previous path Catherine and I went down on. Because I think when we were talking about weights, Greg had mentioned this before too. And so we like did a histogram of the weights. And I like read the literature on this a little bit more. And Twain like like Dan McCaffrey, which is one of the authors and creators of Twing, recognized this because I forget the name of the first name. It was like something Austin. Maybe he's in Texas. He does like propensity score stuff, and he was like, well, you can end up with crazy weights, like someone gets a weight of like 40, and then that can totally throw something off. And then there's like a response paper by McCaffrey saying, well, actually Twing adjusts for that so that you don't have extreme weights. And when we looked at the non-response weights, it was usually between, most of them, like between 0.08 and like 2.5. And then we had looked at sort of the, like what we started to call ATT weights, where we're giving the treatment a weight of 1 and control groups different weights, that they have a larger range in the weights. If you're like saying, what's the ratio of the minimum weight value to the largest weight value? And you were at the time, and maybe still are, uncomfortable with that range because somebody in the control group would say get a weight of 0.2. The other person gets a weight of like 1.1 or like 2.5, and it's many factors over. But I think it's that is pretty common in the weighting world. And my reference was always not the ratio of the smallest weight and the largest weight, but but relative to 1, like how far are you from 1, because you're just trying to get close to 1 or far from 1.
But I don't think that's right.
Yeah, right. And that was the end of the
Conversation.
Right. And
But if you're not that high above, let's say you get a 2, right? But if the minimum's down at 0.01,
that's right.
that's a huge variation, right? So it is about the.
Well, but in some sense,
The
that
ratio.
0.01, if you drop that observation, right, it's not doing anything to the analysis. We're just throwing it out because it's effectively 0, and the weighting is sufficiently throwing it out by just de-emphasizing its importance. So the relative importance to the smallest weight is always going to be exaggerated if you're benchmarking to the smallest weight, but that's effectively a missing observation. And so that's why I don't think the max to min ratio is what matters. But at the end, like I don't remember exactly how this conversation ended, but we're picking up from where we had left off, and I'm not an expert on this either, and so I don't have a good answer. But thanks, Catherine. And so and I think the propensity score people are going to say, well, what's going to matter is whether if you present the propensity score itself, and then you have like overlaps in the propensity scores, and as long as you do, you can just take the portion that matches and then use matching instead. And then like the story continues between matching and weighting. And every time I do this, like the results don't change. And so I've like, all right, I don't know.
So I wouldn't expect there to be extreme weights, even with a 72% response rate and a 10% differential. They'll be differential, but they won't be so extreme that we used to have like a 50-to-1. It was okay to be 50-to-1. But to say that some get really, really small values and therefore are not counted, right? You always hate to lose observations, right? So,
but effectively you're losing them when you give them a weight next to 0.
but
Yeah, and you're losing them because there is no plausible counterfactual. Right? I mean, there's nothing, you can't balance the sample if they're not effectively 0.
So
we throw away the bad observation.
All right, so we can take this as, hopefully it will be as with wave 1, not mattering.
Right. But at least I think I've answered Catherine's question about like, how do we get to the different kinds of weights, which may rely on different assumptions, and you can hold the assumptions constant by stratifying the sample.
Okay, and then
I think Nick has already implemented that into the weighting template and run it, right, Nick?
Yes,
I'm
of
sure.
course.
I saw him scribbling just now, so I'm sure.
Well, while Paul was waxing brilliant about ratios of weights, Nick was doing the work.
My iPad.
I'm surprised he didn't just do it with his mind.
Oh, no.
But
So it's clear to you and Juan Camilo what needs to be done.
Think so?
Uh, all right, more implementation.
I don't know if we scheduled that for.
I didn't.
Yeah.
I have. I
Give us
mean,
a preview of issues.
preview of issues. I've talked about some of them when I've talked about multiple imputation, but the first one is there's like you can do the imputation through a linear regression where like you're just predicting what the missing value should be based on some linear projection or a nonlinear projection, and there are like 15 to choose from. But when I was going through the guidebook of multiple imputation, like very generously provided by the Wisconsin folks on their website, it was funny because like they would go through every explanation of what the ups and downs were of one model, like a logit or like multinomial logit or whatever. And they would say, but if you use PMM, it gives you a similar answer or something like that. And I forget exactly what PMM, it's like something mean matching. It's like it's a flexible model, but I don't really know what it's actually doing.
Non-parametric?
Yeah, it is non-parametric. It is non-parametric. And so sometimes these prediction models won't converge and it'll break. And PMM will always converge. And it doesn't have these crazy restrictions. And so like the moral of the story implicitly told through that guideline was if it's not going to be linear, use PMM, which is what we have implemented. So that's one, as you are creating these predictions on what the imputed value should be, always use linear. And if it's not linear, use PMM. But there are many models you can choose from, and you're free to explore what the model you want.
You're free to run code that runs for 8 hours and then doesn't converge on your own.
And the other is when you have like conditional outcome values, which is something that we had with relationship quality. Like say 500 people are in a relationship, right? And only 400, but you have like say like 700 or 800 people are in a relationship, but you don't know that for fact because you have attrition. And maybe in your non-response sample, there are people in a relationship you just wouldn't know. And so in your observed sample of say 700, you have 650 people giving you some information about relationship quality. And you can try and impute on the remaining 50, right? But there's also going to be in the non-response sample, people in a relationship with potential values for relationship quality that you can't really impute on. And so we try to do this by doing something like, let's then predict if you're going to be in a relationship. So that from the non-response sample, if you have a predicted value of higher than 0.5, we're going to assume you were in a relationship. But that's a bad assumption to begin with, right? Or you can like impute both the probability of being in a relationship and impute the quality of that relationship and weight it by the probability of being in the relationship. But then you introduce a new weighting scheme. Now, one of the reasons why we didn't end up going down this road was the model wouldn't converge and we had these other convergent problems. And I was like, this is a bad problem with a bad solution at best. We're just not going to do that. And nobody really pushed for it once we had reported back on the problems. I don't remember the exact details anymore, but that is one potential problem you can run into as you run into multiple imputation. The other is whether you want like, say your baseline variables are missing, but we have in some of the analytic models just use the mean imputation, right? Instead of doing a multiple imputation. And whether you should use those mean imputed baseline variables to make the prediction, or if you should multiply impute the baseline variables too. And to try and just make this simpler for Sangdo, who is implementing this, I said just use the same exact specification for the analytic model, use the mean imputation, because the mean balance is going to be balanced at baseline. So we worry less about imputational problems. Like the solution we get from mean imputation is good enough because it's based on random assignment. So let's not worry about that. But that would then introduce, but if you didn't want to do that, that would introduce more imputational decisions and more procedures. Then I realized at the end of all this process that if we wanted to do subgroup analyses with interactions, I was now relying on mean imputations at baseline. I've made my life worse, but like nobody, I don't know if people, I don't know what the level of, like the level of missingness was not terrible at baseline, that the subgroup analyses were unlikely to change, but that sort of becomes another wrinkle if you don't do a multiple imputation at baseline, which we didn't under my advisement, which I'm exposing now for all to know.
And what about limits on what variables qualify as predictors?
So I don't think there were any limits. So the imputation model, as I understand it, is it's using baseline information and outcome information to predict the missing outcome or the missing baseline. And
It's supposed to be replicating or pulling from associations across all known information and data. Which is why it has the potential to be really useful, right? So like if you know how the kid did on a matrices, but they fussed out at reading house, it uses the information from matrices to think about what that would look like in other kids for a reading house.
But then that's not just baseline variables.
that's right.
Right. That's correct.
You could specify in the procedure that the predictors are only baseline. You could.
That would be dumb.
Now, the other problem, and so like there's a procedure, sorry, my devices are connected, and this is one of the terrible things that happens. So like for example, the other decision point that we didn't go into, I'm like forgetting now, is we have all the outcomes from the follow-up wave. Do we use all of them and impute on all of them? Like we're doing this for the stress paper, but there are all these like econ outcomes that are in the expenditure paper. If we use that information, the model obviously changes because the predictors are different, but there's more information there, except the model takes a long time to converge. And relatedly, you could do this using not only like say the summary index of an outcome, say the Beck or whatever, but instead use the 57 or whatever, and then impute at the item level, and then average across the imputed items. But it became unwieldy and it just took a very long time. And my prediction was that it would not matter all that much. And in fact, maybe the variation of the latent variable that we're trying to get at by summing or taking the mean of is a better source of variation to be using the prediction for than individually predicted, but I'm not sure. Anyways, so that was like another decision that we had come across. And part of it was like, we need the model to converge. And we were doing this with 20 imputed data sets, which is from the guideline we read on the upper end of things when it was written back in like 2008.
Yeah, now it's the lower end, for sure.
Yeah, because people were doing like 5 imputed data sets back then, and 20 was the recommended, and they were like, some people do 50, but I'm sure now with computing power, they're doing like 500.
I think there's like an upper bound of like 100, 80 to 100, but yeah.
So what is our practical limitation?
Of using, like in terms of time?
Yeah,
So like,
I mean, all the variables in the data set on 100 iterations is not gonna.
it's not gonna work.
Yeah.
Because I think,
Well, and what I go back to is that you don't actually want to impute a data set, because that is completely impossible. What you want to do is come up with like the set of outcomes for a particular, like it needs to be paper by paper. And based on, like, you can augment with things that maybe aren't in our baseline analytic model, right? Prior, like if we're doing CBCL at age 4, prior measures of mom's reports of kids' behavior would be potentially super useful. But you really want to tailor it to the set of questions you're asking. So that's why I think like Lisa was sort of like, well, when will we have a multiply imputed data set? I'm like, never. Like that will never exist. Because it really has to be specifically set up, otherwise it's undoable.
yeah.
And when you do the imputation, you treat treatment and control samples
Together.
separately.
You do it together, but I
But you
suppose,
have to interact everything with treatment control.
right, because treatment is a predictor of your outcome too,
Yeah.
and so it's information. My,
But the interactions are too. It's not just
Yeah.
treatment control.
and I think, but I don't think so. Like, it's not like playing where it's automatically finding different ways to interact all the predictors. It's only using the predictors as you put them in. So you can add the interactions that you want.
Yeah,
But
but
yeah.
you have to have a specification, like you have to have a conceptual, theoretical, analytic model for what predicts the outcome.
Right. And usually my reaction to that is like, I don't know that there's any good one. People come up with many, but I don't know if there's ever a good one. And so I don't
But
know.
what you at least want to do is include everything that's in your analytic model. Like that's the minimum, right? And because you then control for those things anyway. So it's like you at least want that. And then anything extra that you think would be a very good predictor, would allow you to reduce the uncertainty in the imputations and improve your standard errors.
Right.
The world is not but there's limits because you can't put everything else in.
Sounds like the other scores on the other assessments are going to be extremely valuable predictors.
Yep. And maternal reports of in the years prior that are related to behavior, like the peds, about whether moms has concerns and that kind of thing.
So throwing goldfish on the floor is
I'm glad you enjoyed those notes as much as I did.
Throwing goldfish on the floor.
in analysis age 4, there's a set of Excel files with notes that the lab people took for the kids, and it's kind of discouraging.
One of the kids picked up a goldfish and threw it on the floor.
That snack, Paul, the crackers.
What experiment are we doing?
I like the ones where they're like the child intentionally was giving the wrong answers and laughing.
Oh Lord.
And Kim say keep it.
It's probably in I don't know, the robustness check. I don't know. I told her you can't just throw things out because it sounds like the kid didn't like the assessment.
But so if a kid isn't cooperating, right, the scores on all the assessments are likely to be unusually low.
Right.
So they're going to be good predictors.
Is code brown a common code for age 4? I am told code brown is when like the baby or the child like poops during the assessment. And people now have to deal with this somehow. I don't know if we've had an occurrence at age 4, but
Kids are taking a lot of bathroom breaks.
all right.
Within the assessment.
Here's a good one. Started the task. Child would not participate. Threw book on the floor. Went to get a snack and came back. While having yogurt pouch, child completed the task.
Is this from your teaching days?
All right, I have to run, but thanks for including me. I appreciate it.
Thanks, Catherine.
Maria, I just have a quick question. Was there a reason? I know there's like a command in Stata for Lee bounds? Was there a reason you did?
Yeah, so with the command, you can have a model with baseline covariates,
Okay.
So I tried, what I did is I did it manually without the covariates and compare that to the command results and
Uh-huh.
same. So that was just to make sure what I was doing was right.
Yeah.
But the thing is that if you did with a command and then you're creating, and we are mostly focusing on the result with covariates, so it
Mhm.
doesn't make sense because maybe you have bounds and then your effect is like very in the limit or something. So you really want bounds for the estimates that you're focusing on. So
Okay, great. Yeah. Perfect. Well, thanks also for including me. I have to go as well. Have a safe trip,
thank you.
Maria. Yeah. See you, everyone.
Bye.
Bye.
Thank you. Yeah,
Uh,
thank you both so much.
yeah,
Can we stop the recording? Yeah.
Yeah. We don't need the Zoom.